Hello everyone! Welcome back to Historical Geology 1404. Today is lecture 4. It is the last lecture of module 1, which means that the next time we meet in 2 days, we will be having our first exam review. Cool. I'll give you more information about that exam as it approaches on Wednesday, actually. So for now, let's just focus on finishing up module 1. As usual, before I begin, are there any questions that you have? Any events that transpired since our last lecture that are of note that we should discuss?
There was that 7.7 earthquake that Myanmar, Thailand.
There were several earthquakes in Myanmar. Yeah. Did you see the video of the skyscraper falling down? It's like a 30-something story building. It collapsed.
Video of like one of those skyscraper pools basically shattering.
Yeah, the pools, yeah, just like sloshing and water escaping, just tumbling, free falling through the air. Yeah, quite a bit of damage. People were killed. It was unfortunate.
I saw someone jump a breaking bridge on like a bridging skyscraper.
Yeah? Saw someone jump it?
Yeah.
Heck no. Not me. Although I guess that depends on the situation. If the skyscraper that I'm in is falling down, I might as well try to jump to the next one, I guess. Okay? Not to make light of that person's situation. I suppose I did. I apologize. Anything else? No? All right. Any questions about the previous lectures? Anything you've had some time to chew over in the last few days that you want to dive into a little bit more here? No? All right. Well, today we're talking about sedimentary environments. So we talked about Earth as a system. We talked about minerals and rocks. We've talked about igneous rocks and sedimentary rocks and all of those things. And now we are talking about sedimentary environments specifically. Why do you suppose historical geology would be interested in a little bit more time based on, or to study sedimentary environments?
Those are probably the best environments for organisms to be preserved.
Indeed. Do you remember how much of our surface is covered in sedimentary rock? 70%. The vast majority of our planet's surface is covered in sedimentary rock. Sedimentary rock is formed at the interface between exterior cycles, right, and processes, and the geosphere, right? Where the hydrosphere, the geosphere, the atmosphere, and the biosphere all interact here on Earth's surface, that's where sedimentary rocks form and sedimentary environments exist. That is where life exists. So in a class that is focused primarily on studying the history of life on Earth and how it's developed in conjunction with geological processes, naturally, sedimentary environments are very relevant, right? So that's what we're looking at today. So when you look at rocks, and in particular layers of rock, first of all, they can be quite striking, right? The layering effect in some of these is beautiful, right? For example, this little pedestal of rock out here, this is out in Ireland. It's just like a little, like this person's standing on the coastline, and that's just kind of out there, right? Now, naturally, these same layers of rock are reflected on the rock that this person is standing on, but it's easy to see it out there in the ocean, right? I've always thought, every time I see this picture, you see all this nice grass and stuff up there. I thought, how cool would it be to climb this and have just like a picnic up there on that island? I think it'd be pretty neat. Maybe someday. Okay, so these layers of rock represent about 300 million years of history, give or take, if I'm not mistaken, okay? It's been a while since I looked up the stat, but I know this represents a very long period of time, okay? Right there. We're seeing layer upon layer upon layer upon layer. And look, here we have the same layering effect here, but there's something a little bit different in the behavior of these layers with each other. And look, we've got the same layering effect here, but in a totally different situation than we see this one. Same with this. Same with that. You see these different layers on top of each other, each layer representing a different sequence of time during which different processes existed. Those processes are now preserved. The evidence of those processes are now preserved in these layers of rock. Does anyone remember the name that I used to describe the study of layers of sedimentary rock, layers of rock, and their relationships to each other? I'll give you a hint. Layers of rock are often referred to as strata. Stratigraphy. Do you remember that word? I've used it a few times. Well, we're going to talk a lot about stratigraphy today. And yay, your lab 2 is all about stratigraphy. Hooray. Okay, but don't worry, we can work on that together here later on. So, we have two different basic types of environment, okay? Marine and non-marine. Can anyone tell me what marine environment means? What does the word marine mean? Besides a big, scary, buff dude with tattoos that comes at you with an AK.
Water-based.
Water-based? Does it have to, is it all water? The word marine refers to the ocean. Anything in the ocean, right? So when I say a marine environment, I mean any environment that has to do with the ocean. For example, ocean basins, near shore shelves, deltas, which are where rivers empty into oceans, right? And lagoons. Do you remember what a lagoon is? That lagoon where you've got a reef or a barrier island in front of your coastline, protecting a section of water between that island and the coastline from wave activity. That means you have very, very calm water back here, and that's a lagoon. Okay? So those are marine environments having to do with or within the ocean. Okay? Then there's non-marine. Everything from soils, lakes, glaciers, deserts, and rivers. All of these are things that we discussed in 1403. You learned about how all of these processes, how all of the environments, how all of this comes about. Okay? How all of them work, how rivers move, how glaciers are formed, and how they weather and erode material. Right? We learned about all these things. Well, now we're going to apply that to the actual study of those environments from rock themselves. Okay? So let's start by talking about marine environments. In ocean basins, these are your deepest part of the oceans. How much energy is there in deep ocean water? I'll give you a hint. About as much energy as there is in this room right now. What is it, Monday or something? Gosh. Yeah, exactly. There's very little energy in the bottom of the ocean. So, what grain size are we probably going to find there? With what energy? What large amount of energy took large particles there? Remember how this works. Lots of energy can move large particles. Losing just a little bit of that energy, you start to drop out the particles. So before we get to an environment like the deep ocean, we will have already lost so much energy that we cannot... Sorry, I keep getting emails from the college, and I'm just making sure none of them are actually for me. What was I saying? Okay, yeah. So before we even get to an environment like the deep ocean basin, we will have lost so much energy that the large particles don't get out there. Instead, what are we going to end up with? In an environment with very little to zero energy, yes, the tiniest particles, clay-sized particles. And in addition to that, we will end up with a whole bunch of dead stuff all the planktons and zooplanktons and all of the other little creepy crawly critters that live in the water column. Microscopic living things, the base of the food chain, those things are going to die and sift down to the bottom of these deep ocean basins and collect. And that is where we get a lot of our micrite limestones. But before that happens, this stuff is collecting, right? It's collecting on the bottom of the ocean. And there are two different terms that we have for the detritus that is collected at the bottom of the ocean, based primarily off of what the most common ingredient is, you could say. Okay? So these are very, very small particles, either of living things, which are going to be calcium carbonate, right? That calcite shell based. Or they're going to be the silica shell-based organisms. So we've got our calcite-based organisms and our silica-based organisms, depending on what they use their shells. Do you remember what I told you the difference is, where those things show up? Calcite-based shells are in one region of the world. Silica-based shells are in another part of the world. What's the different parts? Where are they? Different temperatures. What temperatures specifically?
Calcite are in warm ocean.
Bingo. Okay. We get calcite-based shells on our organisms that live in warm water, and silica-based shells in the organisms that live in cold water. Why? Because calcite dissolves easier in cold water. And no creature that has survived the evolutionary process for that long is going to have a calcite-based shell in cold water. Okay? So, bless you. When we have a whole bunch of calcite-based shells that fall into the bottom of the ocean, they make what we call a calcareous ooze. I hope everyone is okay with that word. I had a student in my class one time who the word ooze just really bothered her. You know how everyone has that one word? So, like, she had to leave the room in this part of the lecture. Please let me know if you are uncomfortable. Okay, but a calcareous ooze is what we call it when we get a whole bunch of those tiny little microscopic shells that fall to the bottom of the ocean, and they make more or less, it's not truly an ooze like sort of that Play-Doh oozy stuff that you can make with baking soda. That's not exactly what this is, okay? It's sediment, and it's slowly getting more and more compacted, but it's dense. You know, like a good dense clay mud, right? If you've ever made pottery, it's like that, okay? And so it gets denser and denser and denser as more piles up, and eventually it does go on to become a rock. But we call it a calcareous ooze. And then in colder water, when the same thing is happening with these silica-enriched shells, we call that a siliceous ooze. Okay? So a siliceous ooze will go on, it'll become condensed, and it will go on to become chert. Layers of chert in that rock. Flint, jasper, however you want to refer to that. And then our calcareous ooze will go on, condense, get fused together, and become micrite not micrite limestones, but chalks and things like that. Okay? Okay. Oh, right. I forgot to mention, this is happening very, very slowly. Okay? 1 millimeter of this sediment buildup can take 1,000 years or more. That's how little energy there is down there. Okay? But we have these very thick layers of rock made during this process because of how long this has been going on our planet. All right? Okay, so in our nearshore environments, we're going to have a little bit more energy, right? We're going to start seeing things like sand, medium-sized particles, right? Those sands can't be moved without enough energy to move them. And in addition, sand is made out of primarily what mineral? Huh? Salt? No. Quartz. And quartz comes from?
Sandstone?
Well, sandstone is made from sand. Sand is made from quartz. But the quartz comes from? Granite and other felsic igneous rocks, which are only found on or near continents. Okay? So remember, we did this sort of logic train in 1403. Why are there quartz sands only near continents? Because quartz comes from continental rock. Right? You won't have a quartz sand bed out in the middle of the deep ocean basin. Why? There's nothing out there that makes quartz. The quartz is made from igneous rock on or near continents. Okay? So, Tempestites are a very interesting sedimentary structure that we can see. This is a tempestite that you see right here. What do we have? We have a whole bunch of tiny, small particles, clay and silt, slice particles. We've got some sand particles, and we've got large, ripped up chunks of this stuff. Whatever this is, pieces of it apparently got ripped up and put into this tempestite bed here. What happened? Well, an extremely violent, aggressive storm swept through this part of the area, okay? And the deep storm waves pulled the congealing sediment, the densifying sediment off of the deeper ocean, and then mixed it into the nearshore sediment. And so we've got maybe chunks of shale, or what was turning into shale, or maybe some siliceous or carbonate ooze, okay? Calcareous ooze got ripped off from deeper in the ocean, carried inland, and deposited in these nearshore beds of sand. And this is a tempestite. These are very cool because they give us evidence of things like what weather patterns there were. Hurricanes, for example. Every time a hurricane sweeps through, it makes new tempestites on the Gulf Coast, okay? So we can go back through the rock record and find tempestites and be like, okay, this area during this time was experiencing a very similar sort of situation to modern day Mississippi or Louisiana or Alabama or Florida, right? Where it had seasonal hurricane movements. And we can track that seasonality based on tempestites. Pretty cool. Deltas. With a delta, a river has made its way out to the ocean. That's where all rivers ultimately want to go. Why? It's sea level. All water is trying to get to sea level, right? So our rivers are flowing until they reach the ocean. In the case of this, you guys know where this is? Take a guess. Shoot your shot.
Florida.
No, not Florida. Good shot, though. Huh?
Hawaii. Mississippi.
It's not Hawaii. Yeah, well, not in Mississippi. This is the Mississippi River, but it empties out through Louisiana, right? Yeah, this is the delta on the edge of Louisiana that's building out into the Gulf of Mexico, okay? Gulf of whatever it is these days, okay? Okay, so what's happening is our river is continually bringing tons and tons and tons, and I'm not exaggerating, hundreds of millions of tons of sediment a year down through the Mississippi River, depositing it on the front end of this delta, building this delta outward. What you see here, these lighter zones, that is where the sediment is being deposited out underwater. The lighter the zone is, the closer it is to the surface, until eventually it reaches the surface and the land continues to expand outward. The front of the delta used to be here, and it used to be here, and it used to be here. But the river is continually building out into the Gulf, and this is the same for pretty much every delta, okay? So this is what a side view would look like, okay? So our river is here, it's depositing sediment. It's building the front of this delta outward, layer by layer by layer, year after year after year, okay? Pushing out into the ocean. Lagoons. So when we develop one of those barrier islands, let's refresh that. How does a barrier island form? Good. What energy mechanism is causing them to form? Longshore current can play a part. When wave activity is moving sediment, it will typically, your everyday wave activity is going to move sediments along the longshore current, right? But when you have an exceptional circumstance, something like a storm, that storm provides extra energy. That extra energy picks up more sand. It pulls and pushes with that energy sand up close to the shoreline, but that sand piles up into a pile too large to be moved. And so when the storm is gone, it just kind of sits there a little offshore from the coast. And then the next storm adds to it. And the next storm adds to it. And so you eventually get this big old pile of sand that keeps getting added to that can't be moved until it reaches the top of the water. It comes up above the water. And this is what makes a barrier island. So we get these barrier islands just off the coast, okay, in a line commonly. And between each barrier island is a channel where water comes in and out of these lagoons. These lagoons will often empty during low tide. The water will be pulled out at low tide and come back in during high tide. When that happens, we call that a tidal flat. Okay? So when the tide is pulling out, you'll often get a large area of exposed mud out here in these lagoons. We call those tidal flats. There are a whole bunch of very interesting organisms that have adapted to live in tidal flats. I'll talk about those in a little bit. Okay? We actually have barrier islands and lagoons not too far from us. Okay? Here we have Padre Island. Okay? Laguna Madre, I think is this one right here. Okay? So this is Corpus Christi. Okay? This is the Corpus Christi area. All of these barrier islands have been built up just offshore. And between them and the coastline are these lagoons. Everybody loves going and hanging out, vacationing on these islands. It's beautiful. It's idyllic, right? It's awesome. And then hanging out, swimming, fishing, boating, whatever, in those lagoons because they are so calm. Okay? So there's a real-world close example of that. Because there is such little energy in these lagoons, they often get filled up with the smaller particles. So we'll have some sands, but we'll mostly have some silt-sized particles in there. And so we'll often see mudstones form inside of from lagoon deposits. Okay? So if I were to look at a side view of this, I'd see deep sea shales, maybe some limestones, okay, transitioning into sandstones of this barrier island, and on the other side of that, siltstones or claystones in the lagoon before we get back to the sandstones of the beach. And so this is what the stratigraphy, the layering relationship of what those layers of rock would look like. And I can interpret that by looking at layers of rock from a long time ago. I can say, here we have a classic lagoon, barrier island, beach environment, right? By looking at that sequence. All right. Fossils go a long way towards helping us figure out these environments. You've already seen some examples of that. Here I'll show you another one. A large group of fossils in the ocean, we commonly refer to this as a reef. Okay? Whenever you have a whole bunch of organisms living in one place, they build up a giant structure called a reef. You ever seen pictures of modern day reefs? Like the Great Barrier Reef in Australia, right? These reefs exist for a very long time. There's lots and lots of living things, and every time something dies, something melts, starts growing on top of it, and they just pile on top of each other, making massive structures. These structures will often be fossilized, preserved in the rock that gets incorporated around them. They get buried in sediment as time goes on, and they become fossilized reef systems. The Guadalupe mountain range, not that far from us, right? Just across in New Mexico. That whole mountain range is a giant reef system that got fossilized. Okay? So, in this particular instance, we will have, let's say, a volcano. Okay? A volcano forms out in the ocean. Eventually, it grows tall enough that it comes up above the sea level. After the volcano is expired, after it's lived its life, after it's blown its top a few times, right? Its magma chamber is depleted, it's crystallized, no more is coming out, it won't erupt anymore, it can't keep building its structure. So what starts to happen? Weathering and erosion. So we go from this tall, proud volcano in the middle of the ocean, it starts getting weathered away, until finally what happens is the coral reef that built itself around the edge of this island is the only thing that's left near the surface. The rest has been weathered away. leaving behind a circular lagoon. We call these atolls, A-T-O-L-L. Okay? This is an atoll. This atoll lagoon was formed originally around a volcano. And here's a real life one right there. All that's left of this volcano, well, that's above the surface, or near the surface anyway, is the reef. That deep, dark pit, the volcano is still under there somewhere. Just probably really deep. Okay? It's been weathered and eroded away. But this reef has remained near the surface where its organisms need the light. Carbonate platforms are sedimentary environments that form in warm, shallow water. Why warm? Because in warm water is where calcite will precipitate easiest. Dissolves in cold water, precipitates in warm water. So we'll get collections of either little calcite fossils made from calcite, or we can actually have micrite develop. Okay, so little crystals of calcite will precipitate in the warm water and fall to the bottom of the ocean. Some combination of the two is pretty common. But what will happen as time goes on is our warm, shallow water, the bottom will start getting even shallower as this carbonate material builds up and builds up and builds up. Okay, until you're left with water that's maybe only a couple dozen feet deep and pretty warm. Why so warm? Because the bottom of the ocean is so near the surface that that water warms up easily in the sunlight. Okay, so it kind of adds to itself. This effect grows. This is common in tropical environments. Here you see Florida over here, Bahamas over here, Cuba down here. Okay, everywhere you see that is dark blue, that's very deep water. Light blue to white, okay, that's very shallow water. Why is there so much shallow water around all these islands? Because around all these islands are giant carbonate platforms. Very wide, very broad. That's why you can go out to the Bahamas and you can look down and you just see shallow, beautiful greenish water underneath of you in so much of this. Okay? The water is actually maybe only a couple of dozen to 80, 90 feet in places in a lot of this. Okay? Relatively shallow. Stromatolites. A stromatolite is the oldest form of actual fossil that we've got. Anyone remember what a stromatolite is? Anthony's got it on the tip of his tongue.
It sounds familiar.
Anyone else want to help him?
They're like some like disease or something, or what?
Not a disease. It sounds like it would.
Micro something.
Okay, microscopic something. Yeah, bacteria, exactly. So they are layers of algae, okay, which you can think of as bacteria that all decided to start working together, okay? So layers of bacteria that are growing one on top of the other, layer upon layer. Tide goes in, brings sediment. Tide goes out, the algae has to grow up above the sediment to reach the sun. Tide comes in, makes another layer of sediment. Tide goes out, so on and so forth. Okay, layer upon layer upon layer upon layer upon layer, making these stromatolites. And these are the oldest fossils that we have left, or that we have in the fossil record. About 3.5 billion years old, some of these stromatolites. Okay, that's marine environments. Any questions about those? No? Okay. So let's start talking about non-marine environments. Soils, specifically. The hummus joke never gets old, right? Soil is made out of 4 different factors: water, air, mineral content, and organic content. That organic content, we call that humus with 1 M, not hummus with 2, right? Okay, humus. Any combination of those 4 and you'll get a soil. But different parts of the world are going to have different combinations than other parts of the world. Okay? For example, here we have very air and mineral content rich soils, but very little water or organic content. And the plants that live here correspond to the soils. If I took a West Texas cactus and I put it in the Amazon, it wouldn't live very long or very well. If I took a mahogany tree and I put it here, it wouldn't live very long or very well, right? All of these plants have adapted to the soils, and the soils adapt to the environment that they are in, okay? So that mineral content in our soil comes from some form of parent material, that parent material being the rock that it weathers and erodes from. When that parent content is nearby, not far from where the soil is formed, we call that a residual soil. Okay? If that mineral content was transported from somewhere else very far away, say via river, and then that mineral content makes a soil, we call that a transported soil. Okay? And by studying transported soils, we can figure out exactly how far away that sediment came before it became incorporated into a soil. If I can tell chemically, this soil has mineral content that came from granite, but the nearest source of granite is 300 miles upriver, just some good detective work right there. I know how far that sediment was transported before it became deposited. Okay? Our soils, we differentiate them into different horizons. Okay? A horizon being a distinct layer from the rest of them. These aren't rock, right? So I'm not talking about stratigraphy here. Soil is a little bit different. These soils can, given enough time, become layers of rock if they become, compacted enough. But we're not there yet in this process. Our O horizon, very organic rich. That's where all of your plants and sticks and mushrooms and dead squirrels are decaying. Okay? That's your O horizon. Your A horizon is your topsoil. Okay? That's the great potting mix that we like to grow our gardens in. Okay? Most life is in there. Underneath of that is our E horizon, the zone of alluviation. Leaching, right? It's where kind of all of the clays and whatnot that aren't really being utilized get sent. The B horizon is kind of a continuation of the E horizon, except nothing really, it gets compacted, okay? It's like those compacted clays, which makes it difficult for water to get through sometimes. And then we've got our C horizon, which is the material that is actively weathering down, breaking down to make mineral content for soils. Glaciers. Glaciers create sedimentary environments in a couple of different ways. First off, they are really one in and of themselves, being made through a process that's very similar to the sedimentary process. Snow falls, gets compacted into ice, and that ice gets transported, right? Very similar to the sedimentary process. But what they do is these massive, thick blocks of ice also grind and push and pulverize their way through rock, acting as forces of both weathering and erosion. And they leave massive influences on their environment by doing this. Okay? So we can see things like glacial erratics, a chunk of gneiss or granite just sitting there in a layer of sandstone. How'd that get there? There's only one way, right? Either a dinosaur picked it up in its mouth and carried it 400 miles, or a glacier brought it there. Which one's more likely? Right? Then there are things called glacial striations like this, where when a glacier is grinding its way over a layer of rock, sometimes it'll pick up a passenger on the bottom. Okay? If there's a rock here and my glacier scrapes over it, it's going to crush that rock against whatever rock is underneath of it. And it's going to leave a groove in that rock. And that's called a glacial striation. Okay? So we can actually see these in the rock record. If this surface then gets covered in sediment, then I can uncover this layer of rock later and see those layers, those glacial striations, and say, hey, there's a glacial period going on here during this time. This is clearly evidence of glacial activity. Right? Some other things that glaciers, some other landforms from glaciers. Of course, there's the valleys. As they're cruising through the valleys, they widen them out. They crush them smaller and smaller. Or larger and larger, I should say, wider and wider. Cirques are the side valleys that kind of reach into and add mass to these larger main glacial bodies. And then fjords are what happen when those glaciers get flooded, when those glacial valleys get flooded. What's happening to sea level during an ice age? It's what? Lowering, yes. So much water is in ice that sea level drops, which means that as my glaciers are trying to flow to sea level, like all water does, okay, they grind and crush their way, making these valleys lower and lower in elevation until they reach sea level. But then our ice age ends. Our ice melts. What does sea level do? Rises above our glacial valleys. And some portion of those glacial valleys are going to become flooded, making a fjord. Going back to this picture. An arête, remember the long ridges that you see between these cirques and valleys, and the horns are where multiple arêtes come and meet together in a peak. Roche-Montagne, we don't need to worry about that. Glacial deposits, though. Okay, till, glacial till. Sometimes people call it glacial drift. If you know what you're looking for, it can be easy to tell the difference between a tillite and, say, a sandstone or a conglomerate. And if you can make that determination, that's a huge step toward figuring out what the environment was like at that time. If I uncover a layer of tillite in my stratigraphic layers, then I can start to make approximations of temperature change, maybe water precipitation levels, right? The types of sediment that I've got in that tillite are going to be clues themselves as to what kind of rock was being transported by the glacier and was being ground down by the glacier as it went down its path. Also, how far those glaciers went from their source, right? During our last ice age, or I should say during our last glacial maximum, glaciers went all the way halfway through the United States, okay? Down through the bottom of Ohio, right? And further. So, and there have been even larger ones. And how do we know that there have been larger ones? Well, in part due to the evidence of glacial tills, glacial valleys, and other such sedimentary environments that are preserved in the rock. Then we've got moraines. Moraines are these conveyor belts of rock along the sides and in the middles of our glaciers that are being, as the glaciers are moving downhill, all this rock is being transported with it. And eventually it gets dumped at the end of the glacier and makes what we call a terminal moraine right at the end. Okay? So the lateral and medial moraines carry the rock downhill on the glacier and it gets dumped at the end of the glacier and makes a terminal moraine. Any questions so far? Yeah, wherever the glacier is currently melting, it dumps a whole bunch of, like, all that sediment there. And that dumping ground, you can call it, is a terminal moraine. Yeah?
The glaciers in Antarctica, I've seen some videos where people like just get a cup and drink the water from it. Like, is that even safe to consume?
Absolutely. The yummiest water you'll ever have, probably. Really? The water I drank on that glacier in Alaska last year was glorious. The only other place I've had water so pure was in Iceland from a glacier. Loved it. The only possible threat that might happen is some people have postulated that some of the deeper ice in places like Antarctica may contain microbes that we wouldn't be able to handle, basically. And they postulate this because we've actually found some things. Bacteria that are extinct on our world, or that we thought were extinct, but we have drilled deep into Antarctic ice and pulled up hundreds and hundreds of feet that came from millions and millions of years ago, and there's some of that bacteria in the ice. So it is potentially possible that some of that deep ice could have microbes in them from, before the dinosaurs went extinct. And how exactly would we and our immune systems handle that? No idea, right? So right now it's just a matter of a potential issue, but it's definitely an interesting thought. The stuff that's grown on the ice that's on glaciers, like in Alaska or Iceland, where I drank it, absolutely no worries about that. The ice is thousands to maybe 10,000 years old. The ice in Antarctica, though, Antarctica has been collecting ice for about 56 million years, I want to say. So that's a thing. May not be terribly safe to drink or eat that ice. There's a movie. What's it called? The Thing? Isn't it called The Thing, where they uncover like some giant monster thing?
It was like a spaceship, and an alien escaped from that spaceship.
Right. Oh yeah. Oh, so it's a spaceship. Okay, so this is the basis for a lot of movies, right? Alien versus Predator, Temple Trapped in the Ice, right? The Thing, spaceship, The Tomorrow War on Amazon Prime with Chris Pratt, right? The whole premise of that is that these monsters came from a spaceship that was unmelted in Antarctica or somewhere because global warming melted the glacier. It's a great movie, but it definitely came off with it's our fault because global warming unmelted the spaceship. Well, I mean, the spaceship was still there. That's not our fault, right? It may have been there for 1 million years, but it's okay, sure, if that's the moral high ground you want to stand on. Oh gosh, I've gotten like 20 emails so far. These people need to chill out. All right. All right. How we doing? Yeah? Everyone alive? Do you call those bubble braids, by the way? Is that what those are called? Yeah? Those are cool. I like it. All right. Let's talk about deserts. Deserts occur in a couple of different environments. Low latitude deserts are the ones that occur where the dry air that is carried north or south, depending on which side of the planet it's on, meets the surface again. What do I mean by that? At the equator, we have warm, humid air. It rises high up in the atmosphere because physics, right? It's the nature of warm, humid things, they rise. Okay? Water, air, oatmeal, all of it. But what happens next? It gets shoved either north or south of the equator by newer, hotter rising air beneath it. And so as time goes on, it starts to cool off. As it cools off, it rains out a lot of that moisture. A lot of that moisture falls to the surface, and we get dry, cold air that interacts again with the surface at about 30 degrees latitude north and south. That is what makes low latitude deserts. That cool, dry air makes our surface environment more arid. It dries it out in turn. It gets arid by simply not getting enough rainfall a lot of the time. That's what's happening to us here. Okay? We don't get that much rainfall because we are at about that parallel, that latitude, where that dry, cool air comes and meets the surface. Okay? So we get low latitude deserts that way. But there are a couple of other ways we can make deserts. Interior deserts, very large tracts of continents, are arid simply because they are too far from the ocean to receive any of the moisture that evaporates from the ocean. Like the Gobi Desert. As a matter of fact, like this entire area, very dry because there isn't enough moisture that evaporates off the ocean that makes it all the way out there. It's too far inland. When we had a very large supercontinent called Pangaea, and before that one, long before that one, Rodinia, the largest supercontinent we've had yet. When we have these very large continents, there is a lot of land inside that is cut off from the ocean, and therefore it becomes very arid. We will often find evidence that there are large deserts in the middle of these supercontinents. So a lot of life tends to live around the periphery of these continents, and less life towards the middle, except for the bigger, hardier things that can survive without water for longer periods of time, kind of like camels. Like that video we watched about camels last week. right? Camels can go 2 weeks without a drink of water. Well, it's very possible some dinosaurs were able to do that as well, develop that adaptation. And so they could live in the interior, right? Rain shadow deserts, like the Atacama here, block rainfall from certain parts of the continents. If the wind is going this way, then the rain is going that way too. And if it hits a mountain range and it can't go through the mountain range, it has to go over the mountain range, all of that rain happens on this side of the mountain and only the cool, dry air makes it to that side, and so you get a rain shadow desert. Naturally, this all comes down to tectonics. So, what does that mean? If tectonics make these circumstances for these deserts to occur, then finding evidence in the rock record for these circumstances lets us know about past tectonics. We're walking the logic backward. So I am able to make a model like that one from last week where we saw the plates moving around. I can make a model like that not only based off of fossil evidence, but also, hey, this layer of rock present here, here, and here means that there was a massive supercontinent at some point during that time. Because it's a very large desert environment, only possible within a large supercontinent. Or this is a small desert area next to what appears to be a mountain range. Must be a rain shadow desert. If that's a rain shadow desert, where is the prevailing wind direction from? It's coming from that direction, which means it must have been in the southern hemisphere. You know, we can make these sort of approximations based on what we see in the world today. Logic works forward and backwards. When particles are moved through the desert, we would call this deflation. Larger particles tend to remain in place. Wind can't move that as easily. And so the larger particles remain while the smaller particles keep moving. And you'll end up with something like what we call a desert pavement, where you have just a whole bunch of gravel and hard rock left in one place while the rest of the sediment has been moved. You know, one thing that I did with my family this weekend, my brothers are in town. They'll be walking in here in a little bit with their family and my family, because I'm going to give them a campus tour after class. One of the things that I did, though, while my family was in town, is I took them to the Monaghan Sand Dunes on Saturday morning. It was very windy, my friends. I got sandblasted. It was not terribly pleasant. We couldn't actually do that much sledding because going up high onto the dunes, just like, right? It was not great. But what we did do was make some very deep holes in the sand. Yeah. We had 3 different holes going. Mine ended up being the best. Yeah, no, I got a nice hole. It was probably like this big, and I would stand in it. I was able to, it was that deep on me. Yeah, it was pretty good. I was proud of that hole. And then I stood there while all the kids pushed sand back in. And like a dummy, I left my boots on. Yeah, so I was just like, oh, I'll just be able to wiggle, pull my feet up. And then I was like, my boots are on. Oh no, I can't move my feet. So I had to shovel the sand back off of me, about to knee level, so I could get my boots out, because I didn't want to leave them in the dunes. Who knows how many shoes are buried in the dunes because of that. I'm just going to put that out there, okay? Okay, but why did I bring this up? Because my favorite place to go sledding down sandhills in the dunes, you walk out for a while, and there's a very steep-sided dune. It's been there for a while, a couple of years, okay? Very steep-sided, pretty far down, too. And usually, shoom, and it's great. But at the bottom this time, at the bottom of this dune, was exposed bedrock. All of the wind that we've been having lately had stripped, deflated all the sand away from the bottom of the dune until the rock was exposed. So we couldn't go down my favorite dune because there was a hard rock at the bottom and I didn't want anyone getting their face scraped off, right? We're not doing that. So we had to go and find other places to play. But my point is that is an example of deflation. The wind stripped away all that sand, leaving behind the rock in its place. Okay, the rock that was always under there, from which that sand probably came. A ventifact is a wind-polished rock, one that is often aerodynamically formed as that wind is doing that sand blasting effect like it was trying to do on my face on Saturday, okay? Except while my face can turn away and I can leave and go home and rub the sand out of my eyes. I still have sand in my ears, by the way. Like, sand still coming out of my ears no matter how many times I wash, right? The rock can't go anywhere. It stays there and takes that sand blasting 24 hours a day constantly. And so that's how we get the sort of polished, glossy surface that is aerodynamic in the direction of the wind. And a yardang does something similar, except it's a whole rock structure up here that gets more weathered at the base than it does at the top, because the sand is usually pushed along the base of this rather than along the top. And so we get more weathering down here, right? But it's aerodynamic in the direction that the wind is coming from. Okay. Y'all ever been up on the 3rd floor of this building?
Yeah.
You know the picture on the lobby, out by the lobby? We've got this sort of study area out here on this floor, and directly above it is another study area up there. Have you seen that picture?
Is it like the wall?
There's a picture. There's like the TV for that study area, and then there's the picture right here. Okay, my point is, there is a picture of geological nature. It's a picture of beautiful rock formations. And the first thing you're going to notice about it is how you've got these kind of like lovely, kind of almost wave-like structures of rock. And they've got different layers of color running through them. And the people are going to be like, oh, wow, what a pretty rock. But I see something totally different when I look at that. I see an environment. What I see when I look at that picture are essentially fossilized dunes, preserved sedimentary environment from a desert. How do I see that? Well, think about what a dune is. A dune is sand that has been piled up by some force, primarily wind. That force, that wind, is pushing it in a certain direction, layer upon layer upon layer of sand, getting shoved in this direction, shoved up the hill slowly, and then it reaches this peak and then tumbles down the other side. So sand gets shoved up and then tumbles down that side, and gets shoved up and tumbles down that side. And that's how dunes move. These dunes are migrating across this surface in the direction that the wind is pushing them. What would that look like if I turned that into a rock? Layer upon layer of sand in each dune. Each dune, depending on wind direction, and which one's moving faster than the others, piling up on each other. You're going to end up with a picture like what's up there. Let me find that something similar to that here. See if I can find a better picture than that. I mean, that's a pretty good picture. Yeah, that's pretty good right there. The one in that waiting room or in that study area is way better, but this will work. Look at this. You have layers of sand that were deposited at this angle in that direction, right? This is the path that a dune took. Wind pushing it in this direction, right? Layer upon layer upon layer of sand moving in that direction. And then something else happened. Maybe a change in wind direction. Maybe a different dune depositing at a slightly different angle. This is a totally different depositional sequence from a different dune. And then up here, we've got a totally different depositional sequence. Still a slight angle, but much lower angle, right? Something changes between each of these sequences, but all of them represent dunes. These dunes in rock. Okay? So, by studying dunes today and the ways that they behave and the ways that they pile on each other, I can interpret a desert environment from the past. How? Because I can find stuff like this. And by finding stuff like that and measuring angles and grain sizes and how long through time, basically how thick that sequence is, right? I can make interpretations. It's that principle of uniformitarianism, right? Someone pull that out of your memory or off your notes for me. Principle of uniformitarianism. Yeah, that's basically the summarized version. Physical, chemical, and biological laws that apply today, or that are in process today, also apply in the geologic past, right? Also are true back then. Anything that's true back then is still true now as well. Okay? It works both ways. Okay, let's go back here. Okay, so that's what happens to the sand in my desert. What about the smaller particles? The ones that are usually moved by being carried in the wind. Sand can be carried in the wind, as we know here, quite often. More often than not, though, it's getting pushed on or near the ground level. So what about the smaller particles that are almost always carried in the wind? Silts and clays. We call that lust. And that lust can go quite far. This is lust being blown from the Sahara all the way out to Yucatan, Mexico. Okay? That can create problems, bad breathing conditions, but it also makes for very good farming and very dense, compact soils and rocks. Okay? People have carved houses out of it. It's difficult to get into, but once you do, it's very hard to break your structure. Okay? Let's talk about rivers. I showed you this in 1403. I'll just play it again right here while I'm talking. What you'll notice is that as our rivers are meandering around our valley, they're going to extend out. You're going to notice that it's going to bend way far out, and then it's going to snap back to the middle. It's conserving energy. That's how conservation of energy works in nature, right? It's not making the choice to do that. It simply happens because it takes less energy to snap back here to the middle, closer to the middle, than it is to keep building further and further out. Okay? But what's going to happen as this process goes on is you're going to carve out a deeper and deeper river valley, which means that we're going to get wider and wider and wider far-flung loops. And look at this. It's depositing layers of sand and shale. Sand where the river was, shale where the floodplain is. Wherever the river is carving, it's leaving sand behind. Wherever the river isn't, it's leaving shale from the flooding, from the silt and clay size particles from the flooding events. And now here we have our river valley. So I can look at layers of sandstone and silt or clay in conjunction with each other. And if I find what are called channel beds, I know I'm looking at a river. Well, what's a channel bed? It's this shape. Sand left in lenses like that. I'm looking at the cross-section of a riverbed, making that sort of lens shape. Knowing that I'm now looking at a river environment changes up the whole paradigm of my interpretation, right? Shales mean something different when I know that they're associated with a river. Sandstones mean something different when I know that they're associated with a river and not a desert, right? So by studying the structures and not just the types of rock, I can make very valuable interpretations. No, we already saw this. What we just saw was a meandering river. Meandering rivers are not the only kind of river. Meandering rivers happen on very low angle slopes, flat plains typically, okay? Braided rivers or braided streams are what you will most likely get in a steeper environment. Name an environment where I might have a braided river. High energy, lots of motion, steep. Name a steep environment where I might find a river or a stream. Name a steep environment where I might find a river or a stream. A mountain, good, yes. Mountain streams, mountain rivers, mountain valleys, steep angles, right? And so my water is going to have a lot of energy going down through that. As it has a lot of energy, it's going to be able to carry large sediment particles. Good. It's going to carry large sediment particles because it has a lot of energy. Now, as it approaches the bottom of that angle, the bottom of that mountain, it's going to lose that energy and start to drop out those particles. But as long as it has that energy, it can carry the larger particles. Okay? So this is what a braided stream looks like. Okay? So we're going from an uphill, from steep, slowly losing that energy. But as long as we have that energy, we can carry large particles. So what you're looking at here is a braided river. Between all of these different channels of this river are what are called deposit bars. Okay? Those are usually the larger particles that can only get picked up in the floods. So larger boulders and such make up those deposit bars. Okay? But lots of energy carrying lots of particles downstream from this high environment. So you'll get something different by looking at something like this in the rock record than you would by looking at a meandering stream. In a meandering stream, you'll see that nice, neat lens deposit, and it'll have sand and silts associated with it, right? But here, you're going to get big gravels and cobbles, and you're going to have a channel here and a channel here and a channel here and a channel here and a channel here, okay? So you can interpret what your slope is looking like simply by looking at those sort of factors. Okay. Now in lakes, we will refer to these as lacustrine environments, by the way. When you see the word lacustrine, that means it has to do with a lake. But it's lacustrine with L-A-C, not L-A-K. Okay. Okay, so in lacustrine environments, because lakes are typically calmer, what size of particle will you imagine we see in there? Yeah, small particles, with even smaller, finer particles getting closer to the middle, where there's even less energy because it's deeper. Closer to the sides, sand, cobbles, things like that. Closer to the middle, smaller particles. We call these varves, okay? When you have layer after layer after layer after layer of tiny little particles. Now, the thickness of those particles can tell you a lot. Because lakes are fed by streams and rivers and sometimes glacial deposits, however thick your layer of sediment is tells you about how, I guess you could say, how wet that season was. More water means more sediment being pushed into your lake, right? More sediment being pushed into your lake means you have a thicker layer of sediment. So if I have a thick layer of sediment followed by a thin layer of sediment, I can say I had a very wet season followed by a very dry season. I can make interpretations like that. Also, every now and then, you'll find something really weird in your layers of lake sediment. Look at these varves, very thin, very nice, uniform varves, and then what the heck is that? That showed up out of nowhere. This is a layer of gneiss. This is a chunk of gneiss. Sometimes this will happen. Something will just fall in the lake, right? A dinosaur didn't pick this up and chuck it in the lake. It must have fallen off a cliff or something. It fell in the lake and then got incorporated into the sediment because you've got the layers of varves here and then the layers of varves on top of it, and it's just sitting in there. Hi, you can come in. Hi, guys. This is my family coming to visit. You got a lollipop, Michael?
Michael, just gonna see if he's actually
Yes, I need to be inspected every now and then. I need to be checked. Okay, so depending on how dry or how wet our seasons were, that'll determine how thick the varve layers in our lacustrine deposits are. And then you can also check things like pollen that have been trapped in lake deposits. And with that pollen, you can figure out things like what kind of plants were alive at that time and what animals may have been there during that time to eat those plants and things like that. Lake deposits are really cool in a bunch of different ways. But you can see how thin some of these lake deposits are. Look at this penny for scale. Look how thin some of these tiny little layers are, right? So all of this comes together through the principle of uniformitarianism. Physical, chemical, and biological laws that operate today also operated in the geologic past. And operate in the geologic future. And
Past?
we already said the past.
Oh, present.
No, the present's happening now. We already said the future. What's the third part that we add on to this?
Different planets?
Yeah, other places. Physical, chemical, and biological laws that operate today also operate in the geologic past and will operate in the geologic future and are true everywhere else. Okay? So I can look at a dune today and the ways that the sand piles up into the layers to make this dune and the way that dunes pile up onto other dunes, and I can say this was a dune system. This is Aeolian. This is a desert. Look at these cross-bedded sand dunes that were piled on top of each other. And by studying this to understand this, I can see what comes after this to understand what may happen after that. Right? Okay, well, what about the next part? What about that other places thing that I just said, right? What are you looking at? Tell me what you see in this picture. It's brown, you're right. It is brown. What do you guys see? Describe this shape. What does this shape look like to you? It's what? Spattered? Okay. Splattered? Here, let me draw it out. You see something that kind of looks like that. Does that look like anything? With these sort of channels coming off this way? Ooh, what kind of fan? An alluvial fan or? Delta? It looks like a delta, doesn't it? Do you guys remember that picture from a little while back here? Let's go back all the way to... It's really far back. Did I pass it? No, I didn't. It was in the marine environment section. Look at that. Does it look like that? What is this? Where is that? Louisiana. That's the Mississippi River Delta. Let's go back to this. Does that look like a delta? Yes, this is a delta deposit from a river that was depositing out into another larger body of water like an ocean. But do you know where this picture is? This is a picture from Mars. We understand how this forms and what the environment must have looked like when it did on Mars by understanding the ways that these things happen and form here. Okay? And that is how we can apply the principle of uniformitarianism everywhere else in our universe. Okay? Because physics is going to be the same. Obviously, this is a totally different planet. Right? By the way, that Perseverance rover that landed on Mars a couple years back in 2022 is collecting the samples along the edge of this delta. Because if ever there was life on Mars, it was while there was flowing water. And this is the best evidence, this is the best location that we have access to on Mars to figure it out. So those 36 samples, those 36 core samples should be coming back in 2035. And we'll find out if there's fossils in them or not. Any questions? Okay, well, let's discuss our lab really quick. So this is lab 2. Okay, this is what it's going to look like. Okay, so this is your actual assignment. This is a stratigraphic section. Okay. where I give you 3 different columns. Oh, let me erase my delta here. Might be a little bit difficult to see with that. Okay, you have 3 columns of information on a stratigraphic section, on stratigraphic column, okay? So you've got grain size, lithology, and description. I give you some of that data for all of those things. In these first 4 rows, I give you the description. For the bottom 3, I give you the grain size and lithology. So you need to fill in the grain size and lithology up here and the description down here. Well, how are you going to do that? Well, that's why I give you PowerPoints, my friends. Okay. So we go to your Lab 2 PowerPoint, which is on Blackboard for you. Okay, now on this, you're going to have a couple of things that you're really going to want to become best friends with. I go over a few of the basics. Okay, this is how we interpret environments from the data, yada, yada. I give you some example stratigraphic sections. So for example, right here, and this is complete, I have all of this data. Okay, I can see this is the symbol for limestone. So I'm going to write limestone there. And my grain size is going to be whatever the grain size for that limestone was. Okay, this is the symbol for coal. So I write coal here. Well, coal doesn't have a grain size, so we can leave that blank. So on and so forth. This is how we fill out a stratigraphic column. But how are you supposed to know what to put in all these? I give you a key, because I'm not mean, right? So you're going to use all of these symbols to fill in the blanks, so to speak. And where you have lithology data, you're going to use that lithology data, whatever symbols I've put in there, to interpret on the description column what those symbols mean. Okay? So this is a blank. I've already shown you what the actual assignment looks like. Let me bring that up again, just so I can. Okay, so here I say medium-grained sandstone. You're going to find the symbol for sandstone, and you're going to put it in here. This box is going to be filled with the symbol for sandstone. Then, what do you do for grain size? What do you imagine we're going to do for grain size? What's the grain size here? Yeah, it's medium. Good. Okay, where's medium? Right here. So these are gravels, 64 millimeters, 4 millimeters. Then we've got the sand section. Very coarse, coarse, medium, fine, very fine. Then we have silt and clay. So medium grain sandstone, you're just going to draw a line all the way through that row, designating that entire row as medium grain size. Then what do we have? Siltstone. You're going to put this is going to be filled with the symbol for siltstone. What's going to be the grain size for siltstone? Could it possibly be silt? Oh, no? Oh, okay. I'm wrong then. It's going to be silt, okay? So you're going from a medium grain size to a silt grain size, right? So you're just going to draw your line horizontally here. So you're going to be continuing the exact same line for this entire exercise all the way down until you meet up with where I have given you a line right there. Starting right here, you're going to not be doing that, and you're going to be looking at all of this data to give me a description. Okay? So I haven't given you a fill-in-the-blank version digitally. I've given you the Word document because it's way easier for you to print this off and do it by hand. You can do it on your laptop. It will just take a lot longer than it will doing it by hand. Okay? Just to give you an example, the symbol for sandstone is a bunch of dots, which brings me to a really bad geology joke. Okay? Have you ever wondered what the sound of sandstone is? Of course you haven't. It's a joke among geologists. This is what sandstone sounds like. Because that's what it sounds like when you're making it with a pencil on a stratigraphic column. It's just a bunch of dots. Okay? It'll take way less time to do that with a pencil than it will to go dot, dot, insert dot, insert dot, insert dot with your laptop. Okay? So I highly recommend you to print this exercise off and do it by hand. Then you can take a picture or scan it and submit that. Okay? Any questions about this exercise? No? Okay, well, you have about an hour and 20 minutes left for lab time. Feel free to use that to at least think about how to do this exercise. I don't have any printed off for you, and I don't have a printer in my office anymore. work on lab 1 if you haven't finished it yet. How many of you have finished lab 1, by the way? Okay. There's still a few working on it. That's fine. Go ahead and turn that in today. You will have a couple of weeks to do this lab. Okay? So if you can't start it today, not a big deal. I guess I could print off some and then run upstairs and get them. How many of you want to start this today? Yeah, you two go-getters. Okay. 3, 4. Anyone else? 5, 6, 7, 8. You're going to just follow along? Okay. You want to do it? 9. I'll print off 10. I'll print off 10 real quick, and I'll bring them back in, okay? So I'm going to end the recording here and go grab those.